So I'm Jared Stein. I lead higher ed strategy for Canvas, the learning management system. And we are unrepentant data hoarders. We have 16.5 petabytes of data on teaching, learning, and course design, and we add hundreds and thousands of data points every day and provide those to our institutional partners. And yet we recognize this is only part of the story. So I'm very interested in and pleased to introduce this morning's keynote speaker, Lise Getoor. She is the professor of computer science at UC Santa Cruz. So please welcome Lisa with me.
Okay, can everybody hear me all right? And bravo for everybody who made it back from the banquet. I was jealous, that looked very nice. And for this morning's talk, I'm going to kind of cover a bunch of different aspects. I'm going to start off kind of general, and I'm going to ask you to kind of look for where your research and so on may fit in. And then towards the end, I'm going to go into some case studies that specifically are about kind of learning analytics and knowledge discovery and so on. But for most of the talk, the thing that I'm going to be really emphasizing, and I want you to keep in mind, is structure. And when I talk about structure, I'm talking about structure both in the input to kind of learning analytic systems, knowledge discovery systems, but also structure in the outputs. So let me unpack that a little bit. By structure in the inputs, I really mean that, you know, all this kind of crazy data that we can get these days tends to be very, heterogeneous, multimodal. There's different kinds of relationships. You have temporal data, you have spatial data. It's very, very rich. In addition, for the outputs, think of classic kind of structured prediction problems. So things from natural language processing, where you're trying to infer, for example, part of speech tags or something like that, where what you decide one word represents depends on what you decide the other words represent in the sentence. Or something like computer vision, where computer vision, you're trying to recognize what's going on in a scene, what one person's doing, that affects what you think the other people in the scene are doing. Or something like computational biology. And I'm going to, of course, argue also for learning analytics. They all have this characteristic as well. And actually, I really like this quote from Dan Roth from UPenn. And he says, all interesting decisions are structured in this way that, what you decide for one part of the problem impacts the decisions you make for other parts of the problem. But especially for the kind of work that's done in this community, there's this kind of structure, but there's also just the fact that we're dealing with these complex socio-behavioral, technical knowledge systems. And there's all kinds of crazy structure in them. So you think about a classroom and community there, that's probably one of the most obvious examples of it. But then you think about lesson plans and knowledge and kind of the structure there. And you think about, how the curriculum interacts in various different ways. So I want to take into account that there's also this kind of systems view where it's important to think about the structure. And so in this talk, what I hope to do is provide you with patterns, tools, and templates for dealing with structure. And I'm going to go through each of these three things, the little parts of the talk. But throughout, and particularly later on when we have the discussion and so on, the question to have in mind is kind of in the problems that you're looking at, is there structure? And, in what ways are you already using the structure? And in what ways could you potentially use some of the techniques or ideas and templates that I'm going to propose to help you with that? So let me start by talking about patterns. And for the patterns, again, we're dealing with these complex, connected, socio-behavioral systems. But what I'm going to argue is that most machine learning algorithms kind of take this, nicely structured data and essentially kind of flatten it into a table. Wow, my little animation just did not. Okay, you have to see. I worked really hard on that. So, we're all familiar with these machine learning toolkits that take basically a matrix form, and you have to somehow take your data and squish it into a matrix or a table or whatever you want to call it. One of the key issues in doing that is as you flatten it, most of the algorithms then make an independence assumption where each row is treated independently. And that ends up being certainly one of the issues. So when one's doing that flattening and potentially treating these rows independently, oftentimes, not always, but oftentimes you're making an incorrect independence assumption. You're definitely making an independence assumption, and then you have to argue whether that approximation is kind of okay or whether it's problematic. The other issue is the models end up not being interpretable. And so why are they not interpretable? And I appreciate, I saw in the program that there were a number of papers that are talking about explainability and interpretability of models. I think that's hugely important. The reason in this setting is that oftentimes when you do the flattening from the graph structure, you do this crazy feature engineering to kind of map the structure into the columns, essentially. And oftentimes when you do that, you end up, writing some script to do it, or maybe it's an Excel macro or something like that. But it's oftentimes not declarative, so that you store the table data, but you don't store the mechanism by which you computed those columns. And so then that ends up making it hard to reproduce, hard to interpret, and so on. And then the last thing is it doesn't support collective reasoning. And the collective reasoning is the part that I'm going to highlight. If you guys want to go back to these other two issues, I'm happy to talk about those as well. So what is collective reasoning? It's fundamentally this idea that rather than treat any kind of inference as kind of atomistic and independent, we're going to explicitly model the dependence. And we're going to use both kind of whatever local information you have, but also the relational context. So some amount of context to improve the quality of the inferences. And I'm probably going to lapse into using the terminology of prediction, that I'm going to then build a predictive model. But in actuality, I think these are really useful for also discovery and just kind of understanding what's going on in your domain. But further, that I'm not going to talk about it here, but also causal reasoning, because fundamentally, many of the settings that we're in, we're really interested in kind of making interventions and understanding what's happening. I'm not going to highlight that here, but it's something that, you know, my group also works on in the context of kind of these socio-behavioral systems. But I promised that I would give patterns, structure prediction patterns. And the structure prediction patterns that I want to go through are the following: information integration, collective classification, and recommendation. And for each of these, I encourage you to think about what, how they might fit into research you've seen in the conference so far, your own research, and more. And I'm going to be using logical rules to represent them. The advantages of logical rules are they are declarative. They give you a way of capturing structure, and they tend to be more interpretable. And for anybody out there that hates logical rules, be ready that I'm just going to use them for this first part here. I'm going to be relaxing it a little bit later and show how we're going to make these more kind of probabilistic. But for now, I'm going to stick with logical rules because I think everybody can kind of interpret them. So the first pattern is information integration, and this happens all over computer science and data science projects, where you essentially have to match or map between digital references to entities in the real world. So, you know, the simplest example is, you know, you have names written two different ways. How do you figure out that they're referring to the same individual? So if you don't have a unique ID, how do you end up dealing with that? Or you think about like bioinformatic text, where you're trying to figure out this gene that's referenced in this text is the same as this other gene that's referenced in a different document. Or like digital humanities, you're trying to figure out, you know, people, places, and organizations over time. I'm going to use a somewhat topical one that's about the university that I come from, UC Santa Cruz. UC Santa Cruz has a mascot, which is Sammy the banana slug. And I have some documents that are referring to them. And I want to figure out which references refer to the same entity. And so I encourage you afterwards, please help me convert this to a more appropriate learning analytics example, or think of your own. But the idea is that we have some sort of kind of local information. So we have a document, we have some references, and from these references, I'm going to try and figure out what are the things that refer to the same underlying entity, and what's the key structural pattern here. The structural pattern is this kind of, if reference 1 is the same as reference 2, reference 2 is the same as reference 3, then reference 1 and 3 are the same as well. So it's this kind of transitivity pattern that ends up being ubiquitous in these kinds of information integration problems. So this is kind of local information. Now, the relational information, you can have multiple documents. And in these multiple documents, you, again, are trying to figure out what the references are, and maybe figure out that some references don't refer to the same thing. So the red arrows indicate that, you know, here's some article about some guy Sam who owns a restaurant. That's not the same as the mascot. And the kind of rules that you can use here are ones that are kind of more contextual. So they say, well, if I figure out that R1 and R2 are the same, and R1 co-occurs with S1 and R2 co-occurs with S2, then S1 and S2 are the same. So this kind of, I'm going to look and see, is there some similar context? Now, one of the things you're probably thinking at this point is, that's a logical, that's not definitely true. The challenge is all of these are little signals, little noisy signals that you need to kind of integrate in some way, and you need to integrate it at scale. So you have all these kind of little pieces of signal, and then how do you combine it all together, and then how do you do it at really, really large scales? So this is one of the patterns. The next pattern that I want to go over is what we call collective classification, and that's just the idea that many projects require you to infer or make classifications about interconnected entities. And some examples of doing this are that you're just trying to infer demographic information. So it could be something like you're trying to infer gender or other things. I'm going to give and this actually works very well for this, and there, in some cases, too well for this. We'll talk about that in a sec. The example that I'm going to give is slightly richer than just trying to infer in a big network, some demographic attribute of the individuals, where instead looking at some online discussion. And some online discussion where we have people posting something, and then these links are, the red links are that you disagree, and the green links are that you agree. And from this, I'm trying to infer what are the user's stances on a topic. Now, I can, so either pro or anti. I can use, and I want to reference Danya Sridhar is my former PhD student who's now doing a postdoc at Columbia. She was the one that worked extensively on this project. So I can use kind of local information. So this would just be kind of words that occur in the text to try and figure out if someone's pro or anti. So think, you could use sentiment. But then I can use relational information as well. And so for the relational information, I can look at these kind of agree and disagree links. And the kinds of structural patterns that I can make use of are things like if someone's pro and someone agrees with the person that's pro, then they're going to be pro. On the other hand, if someone's pro and someone disagrees with them, then their stance will be anti. And so I can combine these together to collectively infer all of the stances in the, of the individuals. The challenges here, I'm going to get to this a little bit more later, but is privacy. So in this setting, it's all well and good if I want to be able to infer these kind of attributes, but if I don't, then there's issues. And I know that's a topic that's being covered in the conference. I'm going to talk a little bit more about that later. And then the last kind of pattern that I want to go over is recommendation. I'm sure you guys are all familiar with recommendation. Here, the idea is that you need to kind of rank and make recommendations in many, many different settings. And here's a cartoon example of this where I have some user. I'm trying to figure out which items will a user like. And again, I can make use of kind of local information. So the local information that I can make use of is whether or not, if I know something about the topics that an individual likes, and I know what the item is about that topic, then I can say something about the user liking that item. But I can also use relational information, and this is a classic kind of thing that you do in collaborative filtering and other recommender systems. So the idea that, okay, a user likes an item and there's an item that's similar to it, then the user will like that second item. In addition, I can also reason about the similarity between users. So if a user, again, likes an item and there's another user that's similar to that user, then this second user will like that item. So the challenge in all this is, of course, how did you define similarity? So the fact that there's lots of different ways that you could define similarity. There's not going to be one single similarity that will work for all this. So how do I combine them together? So these are some structured prediction patterns. Really, what I like is to do all of these at the same time. So it's not that you do just one of these. It's that you're doing the information integration, you're inferring missing information, you're trying to do recommendations. Like, how do you kind of mix all those together at the same time, do it at scale, handle all the uncertainty? And I've set this up in terms of doing it with logical rules. But logical rules, while they have some advantages, they have some well-known disadvantages. So first off, reasoning with them is intractable. Second off, as soon as you have any inconsistency, things break down. And then I talked about similarities. Representing similarities in logic is challenging. So I want to get to some ways of overcoming these. And so I'm going to offer a tool that allows you to kind of do this kind of structured reasoning. And the tool is going to kind of make use of some of the commonalities. So the commonalities in those three patterns that I gave are that there's some relational structure. There's these kind of complex, heterogeneous interdependencies, and there's noise and uncertainty. So I'm going to describe a tool that we've been developing in my group called Probabilistic Soft Logic. I'm going to put this URL up several times in the next few slides, but this URL has a code, it's open source, tutorials, data sets, templates, and more. But the goal of this tool, and very much it builds on research that has been being done within this community that tries to combine probability and logic. And I've been part of the community for quite a while. I feel like we kind of found a sweet spot in terms of kind of combining together methods and building on methods that folks have been working on for 15 or 20 years. But our approach combines rule-based and data-driven, combines logic and probability, hard and soft constraints, and fundamentally knowledge and data. And so I think it's a really good fit for a lot of your problems. So PSL is a probabilistic programming language for doing these collective reasoning problems. And it consists of weighted rules. So we're going to have rules, but they will have weights now associated with them. And the weights are what allow you to capture kind of soft dependencies. So either you can have hard dependencies, so essentially have an infinite weight that this rule has to hold, or you can have soft dependencies. And a PSL program is going to be some set of rules, some input data, and then the output is a probability distribution. So the probability distribution over all of the things that you're trying to infer. And so what it does is kind of take these disadvantages and, as I'll show in a sec, provides a tractable way of dealing with these structured problems that can handle inconsistencies and can represent similarities. So what does a PSL program look like? I mean, this is an example of the one for that stance problem from before. So you can see, you know, it's pretty straightforward. It's easy to interpret. And I'll show a few more of these just so that you get a sense for them. But what's going on underneath the covers is we take a program, we take some data, and it's now going to define a probability distribution. And this probability distribution has a particular form. It's most analogous to a conditional Markov random field, where the actual kind of mathematical form looks something like this. So we have some distribution, and you know, I'm not going to unpack this here in this lecture. I will, but I did want to show you, for folks that are familiar with these flavor of models, this is just going over all of the instantiations of the rules, some weight, and then this is a potential function, where the potential function captures something about, you know, how much is the rule not satisfied. And basically you want to minimize the dissatisfaction of the rule is one interpretation for it. Now the cool thing is, how did we get to this? Now this would be probably in a different audience. I would go off on like a half hour showing the derivation for how we got to this. I'm very happy to talk to folks who are interested in more detail. And this, I want to call out my student, Stephen Bach, who was very much the lead on this. He's now an assistant professor at Brown. We found this very elegant equivalence between three different interpretations for the weighted logical rules. So one interpretation was coming from the theoretical computer science community around randomized MACSAT, and some kind of old results in that community. Another was coming from the machine learning community, graphical models. Another was coming from soft logic and AI, where there was from the graphical models community these kind of local consistency relaxations that people do all the time, but there wasn't any approximation guarantees. We were able to show certain approximation guarantees could be made use of from the randomized MACSAT community and apply there. So that was actually super interesting. And then the really interesting thing is using, this was our original approach, was using some techniques from soft logic for dealing with degrees of truth. The solution you get there ends up being the same as the solution that you get from the local consistency relaxation and from the max set relaxation. So I think this is really exciting. I think it shows that there's something kind of fundamental to the approach. On the other hand, I think there's still lots of work to do in this space, so anybody that's interested, come talk to me more. But it gives us this way of having one formalism that can reason scalably and accurately across these kind of 3 different interpretations. So PSL gives us ways of doing inference very fast. So rather than doing combinatorial optimization, we're doing a convex optimization. That's going to be a lot faster. Further, we can make it even faster with distributed graph processing. We have methods for learning them. And as I said, it's open source and the tools are here. So let me now give some examples. And I'm sorry that the slides are doing this auto advance thing. That's kind of annoying. Let's see if I can make it go away. Not sure if that did it. All right, PSL examples. I'm going to give you guys 2 examples, and then after that, I'm going to give some learning analytic examples of using PSL. So the first example is about cyberbullying. This is work by my former PhD student, Sabina Tompkins, who's now doing a postdoc at Harvard. She built a model that's interesting in that, you know, like many methods for detecting cyberbullying, part of it is just to, you know, figure out which messages represent bullying messages. But then on top of it, she was trying to look at the kind of underlying dynamics and use some of the theories from work on bullying about roles. You know, you have the victim, you have the bully, you have supporters, and so on. And then what kinds of attacks there were, and being able to discover the kinds of attacks, and then reason collectively about all of these together. And you know, here's a part of the PSL program for cyberbullying, and then some results where this was on detection on Twitter data. And one of the key findings was incorporating uncertainty was beneficial, partly because, you know, you have a tweet. It's like, is it bullying or not? So being able to incorporate that kind of uncertainty about the label ended up fundamentally increasing the performance of the system. And so compared to a published state-of-the-art method, we were able to, by using this richer model, increase performance significantly. But again, I think the more interesting thing is around the kind of discovery aspect. You know, what can you then discover about the social systems, and then how could you use that in a more sophisticated way? So in this, there was some evidence of power dynamics that she could pull out, and also we could do things like discover what's the most common attack type, and so on. The next example that I want to give of a model that's, richer than those patterns that I gave at the very beginning is a social trust model. And this, my former postdoc, Bert Wong, who's now an assistant professor at Virginia Tech, was the one that did the main work on this, where in this model, we're looking at individuals and we're looking at trust are the green edges and distrust are the red edges. And, there's existing work in social psychology around different models for how trust forms in these networks. And one of them is the structural balance method, and one of them is the social status. And for the structural balance method, this is the kind of classic, a friend of a friend is a friend, enemy of my enemy is my friend. And, there's all these different combinations of trust and distrust relationships where you look for consistency across them. And the cool thing is you can encode those as PSL rules. The second model that's popular is what's referred to as a social status model. And the social status model, again, it's this idea that, I look up to people that are above me in the hierarchy and I don't trust the people below me in the hierarchy. And again, this turns out to have certain combinations of trust and distrust links that make sense, that are consistent with this model. They're a little bit different than the ones for the balance model. And the cool thing is, we can throw these into PSL model. We can evaluate them. In this case, the evaluation is on predicting the distrust links, which are the ones that are harder to predict. And we have our two models, the PSL balance, the PSL status, two state-of-the-art methods that were kind of network science-y approaches for doing this, and a baseline model. And the interesting thing is, both of our PSL models did better than the competing methods. But then the thing that I particularly liked about this piece of work is we next went on to build on this, where we introduced a latent variable. And the latent variable is about the individuals, and the individuals in terms of how trusting they were or how trustworthy they were. And so you add that into these two existing models, and the performance you get with the latent variable model is significantly better. And so then this is the place where you would then go to a domain scientist and say, like, oh, in your organization I found, the engineers are all balanced over here, the the bureaucracy types are more hierarchical over here, and how do you mix them, and how do you figure out looking at the trustworthy and the trusting individuals, and what does that say about the organization? So we've actually worked on a lot of other PSL projects. Any of these, I'm happy to talk to folks offline about stuff in bioinformatics, energy disaggregation, more on recommendations. But I'm going to go into templates now and pull out two of these that are the modeling student engagement and the knowledge graphs, because I think they will be relevant for this community. So within the templates, I'm going to talk about modeling engagement, knowledge discovery, and then a little bit about responsible machine learning, all in these kind of socio-behavioral settings. So for modeling engagement, this is very much work of Artie Ramesh, former PhD student who's now an assistant professor at SUNY Binghamton. And she's done a whole line of work, which I'm going to kind of pull out some little pieces of for you. Again, happy to talk in more detail about each of these. But the first one is just about modeling student engagement. And so this is modeling student engagement in MOOCs. And clearly, the ways that students engage in MOOCs is different than classrooms. The thing that was nice about this initial work, which was from more than 5 years ago, is we were able to validate our methods on 8 very different MOOCs that were done at University of Maryland, where I was a professor at University of Maryland at the time we were doing this work. And if you think about MOOCs and student activity, they have exactly this kind of rich structure that I've been claiming that PSL is good at modeling. And so you can think about all of the ways in which students engage in a course. So students engage by, doing homeworks, taking quizzes, doing assignments, and so on. But they also have these kind of behavioral aspects where they kind of view the lectures, they post and view on the forums and so on. And then you can look more at the posts themselves and do some content analysis on them. And so it's very rich. And one of the pieces of work that she did, the one that I'll go into in a little bit more detail, was looking at how you can take a system like this, and then we are going to use it for this kind of predictive evaluation, but still I think that the part that's interesting is this kind of discovery of what are the features that go into this and so on. And the performance, we had course performance, which was around whether or not they got a certificate in the course, and then course completion. Lots of people start these courses, but how many of them finish them? And similar to the social trust example that I just gave, we're going to introduce one model that has latent variables, where the latent variables capture something about the student activity. And again, what we're putting in is super, super simple. You can get much more sophisticated, but the fact that even the simple distinction and latent variable that we're putting in ended up giving us a boost in performance is interesting. And the latent variables were around engagement. So whether you're actively engaged, whether you're passively engaged, or whether you're becoming disengaged. And just to give you a little bit of a sense of the models, the ones that were these direct models that didn't have latent variables were things like a whole collection of observed features. I won't kind of bore you with going through all of them, but again, think of them as these little noisy pieces of evidence that go into the model. For example, if student John posts something that has positive sentiment, then maybe that's a indicator that they're more likely to complete the course. And you can think of complete the course and or get the certificate. We had both versions of these things. Or a version where you can vote on something. And so if you vote for something that has positive sentiment, and you can kind of think of all the different ways that you could expand out from here and construct these kind of signals. So that's one component of the model. The latent engagement model then adds in this notion of active engagement, passive engagement, and disengagement, and combines those together. And so again, there's going to be things that indicate active engagement and things that indicate passive engagement, things that indicate disengagement, and all of those are combined together to indicate course completion and course performance. And so the empirical evaluation we did across several different disciplines and different instantiations. Again, I'm going to show you a snippet of some of these results. The data set contains all of the information about the student activities. It contains information about interactions, and it has the assessment data. And this first set of results is around predicting whether or not they get the certificate or they don't get the certificate. We had a baseline which actually worked relatively well, so keep in mind if you don't want to do anything as fancy as PSL, these things of just looking at basically how many lectures did they watch, and their lecture viewing was quite, had a lot of signal in it. And then adding in the kind of direct model and the latent model across, these were the three largest courses. We see improvement along different measures. So for predicting either of these or a combined rank, which mixes both of those, we get an improved performance. For course completion, which is kind of harder to predict in many ways because so many people drop out, again, we get an improvement of performance, especially across the completion part, and then predicting dropout and the overall. Then another use case that I already identified was all these things are important to predict, but one of the things that's interesting is how do you predict them early? So being able to predict early into the course, at the start, the midpoint, or further on, combining these two, how well you could do at predicting who's going to complete, so then ideally you can make some intervention. Again, this latent model did well. So this is just kind of a sprinkling of the results from these. I have like a lot more slides here that I hid. If you guys want to, there's some stuff that's just really interesting about the basic analysis of the data and so on. I'm happy to talk about those. But I want to talk about a second component of Artie's work where she did kind of more fine-grained text analysis of what was happening in the forums. And for this work, again, she did a bunch of different things. I'm going to highlight the kind of first one, but one of the last ones I won't talk about so much is the evolution of topics over multiple instantiations of the course and so on, which was interesting. But this first one, sentiment towards course aspects. The thing that I liked about this was originally motivated by a conversation that I had with some educators saying, like, you know, looking at sentiment is fine, but you do realize that it's a pedagogical strategy to, you know, get students to engage by having them have kind of strong positive and negative reactions to the content. And particularly in certain disciplines, this is, you know, your strategy. You want to get them engaged, so you want to get them reacting strongly. And so they were saying, like, well, engagement, you don't want to look at, like, negative sentiment does not indicate disengagement. Oftentimes it can indicate strong positive engagement in the course, even though the sentiment is negative. So what we were trying to do in this work is kind of pull out, you know, from, these are some sample posts, trying to both look at sentiment, but then sentiment towards different topics. So here, you know, we can say the sentiment of some of these are positive, negative, or neutral, but then what are the aspects that the sentiment is towards? And so looking at, some of them are towards academic aspects, and so in that case the negative sentiment may actually, you know, be a sign of positive engagement, versus some of them are for the logistics. And, you know, figuring out that the negative sentiment is for the logistics is something like, okay, well, that's something to indicate, like, okay, those are things that you could go in and focus in on improving and so on. So in this work, she was able to show that, you know, by doing this, one validation was that we were further able to improve our performance at predicting completion. But again, I think the more interesting thing is kind of teasing out these aspects of the performance or of the socio-behavioral system. And so the last piece of work that we've done in the space of MOOCs was by Sabina Tompkins, who I mentioned earlier. This was interesting because it was on a high school MOOC. And high school MOOCs are, you know, quite different for a number of reasons. There are some structural reasons that this is interesting. For example, it's a year-long MOOC. In this case, it was for computer science. They were to take the AP test at the end. So you kind of had this, whether they passed the course versus whether or not they passed the AP test. So you had these two aspects to evaluate. And then there were, I mean, the first set already had complex dynamics. This had even more complex dynamics because some of the courses had coaches, and so you could look at the performance of the coaches. And in many cases, there was a coaching forum, so you could see what was happening there. And so there was a kind of complex and different ecosystem to just analyze. We did a fair amount of work there. And then we again used a PSL latent model to try and tease out some of the behaviors. And the behaviors that we were interested in looking at were student collaboration behaviors. Sabina kept trying to call it cheating, and I told her, no, you can't call it cheating. But there was some evidence. We were trying to understand what was happening where we had unexpected high learners and unexpected low learners. So things that the models were making mistakes on, and then, you know, what was going on with those. And we were able to, again, have a latent model that tried to discover these peer effects and model the strengths of the students collectively. And more details about this work appear here, and then there's some more that's currently under review, but this had interesting dynamics. The other project that I think is relevant to this community as well, a little bit different, is work on knowledge discovery, especially knowledge graphs. This is very much work by my former student, Jay Pujara, who's now assistant professor at USC, where the task is, you know, go back to the information integration example. You're trying to take this text data where you've extracted facts, they're all really noisy and interconnected and so on, and from that construct a knowledge graph. You want to do this at scale, you want to enforce ontological constraints and kind of integrate the different confidences that you have in the extractions, and do this all with PSL. And so the cool thing is we can write, again, a surprisingly simple looking PSL program for this. Jay did this across 3 different knowledge graphs. NEL is one of the best known from academia, from CMU, but then 2 that he worked on while he was at Google, Freebase and Music Brain. And he was able to show that we could build a PSL model where we mix the use of just the data, so the statistics, versus the ontology, and taking into account doing entity resolution. And we do very well, and combining them is important. So combining the data and the domain knowledge is important, and we can do it fast. So we can do it for large knowledge graphs in, minutes rather than days, which was what the competing system was doing, or just wasn't able to do, as you can kind of see. We also looked at embedding methods for doing a slightly different task. Rather than constructing the knowledge graph, just doing knowledge completion. And the interesting thing here is the embedding methods, they work great when you have a lot of data and it's not noisy. But when it's noisy and when it's sparse, that's the place where PSL really benefits. And I would argue that, that's usually the real world setting, is that you have noisy and sparse rather than clean and large. So the last thing that I want to comment on is responsible machine learning, or responsible data science. And I'm going to call this kind of the perils of ignoring structure. I think it's really important as we build these data-driven methods that we take into account structure. One way is in terms of privacy, and I mentioned that earlier. I saw that it's mentioned in the program. Privacy in particular, when you have this relational setting, you can do all you want to hide attributes of an individual, but if you can infer them from other individuals or kind of inadvertently infer them from things that are correlated and don't take that into account, that's a really serious issue. And so we've done some work in this space. I'm happy to talk more offline about that. In particular, Elena Zaliva did some really nice work on actually on Facebook kind of data. You know, this was like 10 years ago, showing like how much information is leaked by group memberships. Another place where responsibility is important is fairness. So I was glad to see, you know, one of the best paper, and there were lots of other papers in the conference on fairness. I think fairness in the structured setting is particularly interesting to discover different kinds of patterns where the patterns may actually be kind of structured according to some social group or economic group or so on, and being able to take that into account. And then finally, this topic that people often refer to as algorithmic discrimination. So the idea that you can take an algorithm that's biased. Now, because it's biased, then you're operationalizing that bias and oftentimes legitimizing it, because it's like, oh, well, the algorithm is the thing that's said to do this and so on. And then creating this kind of feedback loop and being able to uncover that, and in particular, uncover that in an education setting is, I think, really important and fascinating. And I think kind of thinking of the feedback loop as that kind of structural component is important. So to close, I have to do the most important part, which is acknowledgements. So, you know, the best thing about being a professor is all the awesome students and collaborators you get to work with. So my group, Lisa's Inquisitive Students, are a huge part of everything that I've presented. A big thank you to folks that have sponsored my work. And to close, I hope that you've come away with some kind of tools and templates, some thoughts about kind of structure and how you might use it. I think there is this real opportunity for methods that mix kind of data-driven and knowledge-based approaches. You know, I've proposed one. I think there's other ways of doing it, really thinking about how do you kind of mix the two in interesting ways. There's a huge number of applications in learning analytics and knowledge systems, and doing it responsibly is key. And so I think there's opportunities here. So thanks.
Thank you, Lise, for this very, very rich and interesting bouquet of methods and applications, examples. I think we have just time for 2 questions before the coffee break, and then there is the Q&A. So.
Thanks for the great talk. It was really interesting, and I really enjoyed it. And this is fairly new to me. But we've faced the problem a lot in some of the data that you, similar data to what you've pointed out, where there might be 50 indices that are within an algorithm, and I suspect, well, okay, it's X and Y equals good, but X, Y, and Z equals bad. or, all these complex, I suspect them, but I've never been able to actually, these interactions, I find interactions in my data, but,
Yeah.
but one of the questions I have is if you could point us to some papers that tell us how to discover the structure within the data.
Yeah, so I can certainly answer the question for our setting, which I didn't go into that much during the talk, but we do have methods for learning the weights of the rules, and then what's called learning the structure of the rules, so searching over the space of possible rules. I do think exactly when you have a domain expert or someone familiar with the setting that can provide some starting point, but then you do it in a data-driven way where you both, check the weights that you learn from the data, then expand on the structure and kind of complete that loop is beneficial. The cool thing is, I think this family of methods allows you to do that at scale. So you can search a lot of different models quickly. But then a part of responsible data science to me is then, okay, you get out your model and then, drill down on it and, do more additional testing of it, do comparative analysis, like if I compare it with this one versus this one. So I think there's a real place for this more flexible meeting of knowledge about what you think the interactions are with the data-driven piece of it, and then checking whether it transfers. So I didn't talk about it, but the models that Artie built, she trained them on one setting, but then tested, did they generalize to other settings as well? So.
Thank you for the great talk. Couple of things is that again when it comes to stochastics versus non-stochastics, the randomness, are you using hidden Markov as well as naive basis? There are a lot of statistical. Are you doing some transitional probabilities? My larger question is like a drug-to-drug interaction. I have done so much, but when it comes to the learning analytics point of view, the randomness, like what is your sample size when you try to converge more and more, how this model's successful versus failing?
Okay, so I'm going to answer, but double check that I'm answering your question correctly, that I'm interpreting it correctly, because I think there's multiple places where stochasticity and randomness come into these kinds of models. And one answer is that the way that we do inference is not a sampling-based approach. And actually, that part is cool. That is why we're able to scale much, much larger than, there's nothing wrong with them, but it's a different class of problems where you do the sampling-based inference. That's the cool thing about the optimization that we got. We're doing direct optimization of that. So then some of the classic statistics kinds of questions don't come up in quite the same way. So there's different flavors of questions that you need to ask. And like a lot of machine learning, we tend to validate them through doing some form of cross-validation and then looking at generalization and so on. So it has a different flavor.
Thank you.
Yeah.
Thank you. And There is more time for questions after the coffee break, so thanks again.